Hello everyone, my name is Diego Lopes, I'm from Belém of Pará, and I will present what we have been researching over the past few months. I would like to thank the event's organizer and everyone who is participating of 8th Brazilian Congress of Thermal Science and Engineer. Thus, the present research theme is Solution of the Richard equation in a soil profile with two layers using the methods of line. Autores are Diego Souza Lopes, Augusto César Cordeiro Jardim, Diego Cardoso Estumano, Emanuel Negrão Macedo, and João Nazareno Nonato Quaresma. And during the presentation, we will see the following topics: a brief introduction, the mathematical formulation, and the solution methodology, and results and discussions, and finally the conclusion. So, the main physical phenomena to be studied are the infiltration and movement of water in the soil. Both are important topics for the study of the hydrological cycle of vegetable ecosystems. In such events, the ability to infer soil moisture and its interaction with vegetation has excellent practice in hydrology, engineering, soil science, water resource management, and mathematical modeling. Generally, the process of infiltration into the soil is presented by the Richard equation, which presents an advection diffusion terms derived from the mass conservation, which generalizes Darcy's law to the saturated flow in the porous medium. Soils, in turn, are inherently heterogeneous at different scales. Usually, soil profiles show layered characteristics, which have a major influence on the phenomenon of infiltration, redistribution of water, and moisture in the soil and the groundwater recharge. Hydraulic properties, such as unsaturated hydraulic conductivity, can vary in magnitude in different layers, while soil moisture can be discontinued at the interface between layers. Their characteristics pose the change the numerical solution of the Richard equation. In the generally, the theta form of the Richard equation, where theta present in the water content, is not used for the layered soil, as there is a discontinuity in the value of theta at the interface. Hughes et al. In 1989 were the first to develop a numerical solution for the theta form for the infiltration into the layered soil profiles. And for the solution this problem, the followed hypotheses are a model for infiltration of water into a two-layer soil, a single domain approach proposing a transition function at the interface between layers. Dependency on hydraulic conductivity is given by the Gardner model, and the mathematical formulation for the Richard equation in the theta form accounts for the effects of saturated hydraulic conductivity on the diffuse flow of the water that are also evaluated in the terms of the soil weighting cycle hydraulic pressure extended along of the soil profile. In light of this, the methods of line mole approach was used together with a finite volume scheme, FMV, proposing a mesh with elements of centered volumes, with a regular and fixed mesh to numerically solve the system of partial differential equation PDS of proposed model. The application of model resulted in a system of ordinary differential equation, ODS, which are solved numerically through the development of a code base on the Fortran programming language. And numerical results were generated for the water content and hydraulic pressures 8, showing the weighting front across the two layers soil profile at different times, and the effects of the saturated hydraulic conductivity vary along of the soil profile. The solution methodology used in this work will be validated with the results obtained in literature. And the mathematical formulation. The Richard equation that governs govern the vertical, one-dimensional, and transient flow is in saturated soil is that form is given by for this equation. And equation 1 is the main equation, and the equation 2 is a initial condition, and equation 3 and 4 are the boundary conditions, where the function k is a hydraulic conductivity, d is a hydraulic diffusivity of the water in the soil, which follows the relationship is given by the for this relation, where c is the water capacity of the ground of capacity of the ground, and h is a hydraulic pressures. Z is a vertical coordination defined as positive downwards, and T is the time. The flow governed by the equation 1 will be solved under the effects of a constant flow on the surface Ts and a saturated lower limit Ts, with the presence of continuous flow conditions at the interface between layers, with an initial condition T0, which is the steady-state solution of equation 1 in terms of that with an infiltration rate Ki at the interface Z equals 0. And the schema of the single domain formulation and can be seen in the figure 1. And the hypothesis of solving the problems of a double domain in a single domain consisting of combining the equation that govern the two regions in the exclusive set of the equation valid for the entire domain. For this purpose, a transition function for Ts is proposed concerning the position expressed by the equation 5, where Ks1 and Ks2 are the saturated hydraulic conductivity of the soil 1 and 2, and f is a function that represents the transition coefficient expressed as follows the equation 6, where z1 is an interface position between layers, and delta z is an interval between one point and another on the median, and omega is a parameter of the transition, which is related to the amplitude of the transition curve. Equation 5 is proposed to make Ks continuous. This in turn is caused by the imposition of the capillarity force called capillary barrier, which is a result of the variation of the physical properties of each soil. And for the hydraulic functions, used the function of Gardner, proposed for Gardner in 1958. The following these functions, where that S and that R are their saturated and residual water content. Ks is a saturated hydraulic conductivity, and alpha is a pore size distribution parameter. Given the relation of the equation 8, the hydraulic function for the that form, the Richard equation, are for these equations. The initial condition is steady-state profile for the initial constant flow, Ki, is with the transition function introduction into the solution, given by the following expression. Equation 12 for the TAT is single domain solution that can be generalized for n soil layers. The introduction of transition function is used to smooth this discontinuity at the interface. And the methodology of solution is followed the steps, and defining the problem and the first is defining the problem and its conditions, application of method of line with a finite volume scheme, obtain the ODS system and a computational resolution, and finally the results, numerical results. And here is the scheme of domain discretization, and the ODS system resulting from the application of the mole process is given by. And for this all the systems obtained um, the, before the application of the mole and resultant discussions. The present the input data which are theoretical soils proposed by Srivastava and Yeh, and the soils parameters for given this table 1, and values of hydraulic parameters is table 2, and a convergence analysis performed to evaluate the computational performance of the solution. Different values are the test for in Z, and in different positions along the profile Z, 4 times t equal 1 and t equal 100 hours. The values refer to theta, present in the table 2 and 3, and the objective for the building the convergence table is seek a numerical convergence for the water content in the soil, and to know the permissive of the developed code. Not that good convergence is found near upper and the lower boundaries, and for intermediate position a large NZ value was needed, so it was used z equal 0.5 centimeters. It's sufficient for the both times. In z equal 400 is the value for the simulated mesh cases. And the figure 3 and 4 provide a comparative analysis between the solution results obtained the mole for diffusivity flow of water in the soil in terms of water content and hydraulic pressures. The solution obtained in the term of theta for the Hessian equation. It is used to obtain hydraulic pressure values through its relation given by equation 9. Cite the analytical solution given by Srivastava and Yeh in terms of hydraulic pressures, so it can be compared in an analytical solution with the method of line. Figure 3 and 4 show the weighting and pressure profiles at different times along 2 layers of the soil. The boundary conditions are the same for both cases. The present profiles present the effects of key S on the layer size. Key S is a physical property which represents the hydraulic conductivity of the soil. Is the property of the porous medium, which translates the speed with which a given liquid passes through that medium. And in this work, a theoretical study of the water infiltration process in the layers was developed, in which the Hessian equation was used to describe the mathematical formulation of the problem. A linear function for the hydraulic conductivity was used as strategy to overcome the problems of the discontinuity at the interface between the soil layers. We applied the mole approach with the scheme FMV to obtain a system ODS that was numerically solved through code based on the Fortran programming language using the debug subroutine from the EMC library. The excellent agreement of the present result with does in the literature demonstrate that approach with a single domain used in this work was adequate to model infiltration of water in the soil profile with 2 layers. And acknowledgements, and thanks for watching.